Okay, welcome everybody to this session that we have today. So we have Antonio Sollima, which is currently a postdoc here, presenting a new result that he has published recently about the binary population in galactic globular clusters and comparing his model with the observation. So go ahead.
Bien, gracias, Ignacio. Hola a todos, soy Antonio Sollima y trabajo aquí al Instituto de Astrofísica de Canarias desde el mes de diciembre. Me gustaría mucho hacer esta charla en español, pero mi español, como puedes escuchar, no es tan bueno de hablar de ciencia, entonces mejor que hago en inglés. Pero si quieres, puedo hacer la pregunta en español porque no entiendo bien. So, let's switch in English. Today I will show you some of the most recent results I obtained, together with the stellar group of Bologna, regarding the study of the binary population in globular clusters. And so, few words of introduction. Binary stars are very important in astrophysics, since binarity under particular condition can determine the fate of low-mass stars, like, for example, in the case of explosion of supernova 1A. And moreover, binary stars are on the basis of the formation of a number of peculiar objects like blue-streak stars, low-mass X-ray binaries, or novae. In particular, binaries are those systems which, under particular conditions, it's possible to determine the masses, the luminosities, and the radii of the component of the binary system. And so, in the past, this allowed to determine important relations for stellar evolution, like, for example, the mass-radius relation, and to use them as standard candles to determine astrophysical distances. But the importance of binaries is also evident in collisional stellar systems like globular clusters, since they can provide the gravitational fuel that can halt and even reverse the process of core collapse of this system. Now, the abundance of binaries in the local universe have been estimated to be about 50%, but this value is subject to a large uncertainty that is linked to the method how this fraction is derived. In particular, if we see the binary system formed like a massive components, primary components, surrounded by a small companion, so the companion can perturb the orbits of the primary component, and so this can be visible in the radial velocity curve like an oscillation. This is an example of Duquesnoy-Mayor 1991. And so the way to determine the fraction of binaries is to observe spectroscopically a number of stars in the solar neighborhood and to look for a kind of variability of this kind. The problem is that there are two important biases that are the first when the companion is too small and so produce a perturbation that is negligible and cannot be detected. And so this produces a bias toward the detection of high mass ratio binaries. And the other problem is related to the period distribution, since there are theoretical arguments that indicate that could exist also binaries with period up to 10 up to the 7 days, that is about 10,000 here. So in practice it's impossible to follow the evolution of the radial velocity for over such long time. And so this, the fraction that can be derived by this analysis have to be corrected by using distribution of mass ratios and periods that are chosen in an arbitrary way, and this produces so the large uncertainties. The situation in globular cluster is even more complicated, since binaries in globular cluster can be formed and destroyed via interaction between single stars and binary stars. So in practice, the fraction of binaries that we can determine now is different from the primordial fraction of binaries. Up to now, the prediction of the binary fraction in globular cluster performed with the same method that we learned before are related to just few clusters. I found only these 4 examples in literature. And the main evidence is that the fraction of binaries in globular cluster seems to be a bit lower than those observed in the field. But however, even in this case, the uncertainties are very large, and in particular since we don't know if the same distribution of periods and mass ratios can be applied to the field and to the globular cluster or to different kind of globular cluster. But this is not the only way to determine the fraction of binaries in globular cluster, since we can use also the coordinate diagram of this system to give an estimate of this fraction. In particular, here I plot the mirage line of globular cluster and the location of a star with mass M1. So if we observe an image of a globular cluster, we cannot distinguish the components of a given binary system since the separation is too small. And so we observe a single object with a flux that is equal to the sum of the fluxes of the two components. So in the case, for example, of a binary system formed by two twins with equal mass, the object that we observe will have a magnitude that is, appears to be brighter than the magnitude of the dominant component of a quantity 2.5 log 2, that is about 0.75. And so it's clearly visible toward the brighter part of the current magnitude diagram. Of course, if the mass ratio is lower than 1, the binary system follows a track that is closer to the cluster main sequence as the mass ratio is smaller. So a way to determine the binary fraction here is to do a simulated current magnitude diagram by assuming a population of single stars that populate the cluster ridge line and a population of binaries once assuming a distribution of mass ratio. And then by comparing the simulated current magnitude diagram with observation, it's possible to give an estimate of the fraction of binaries in globular clusters. Now, we try to apply this approach to a sample of 13 galactic globular clusters that have been observed with the advanced camera for survey on board HST, and this has been published in a paper, Sollima et al. 2007. This is, the sample is, of course, consists of cluster of a given type. In particular, all these clusters have low central densities to allow a good photometric accuracy also in the central part of the cluster. An high galactic latitude to avoid the field contamination that can contaminate the estimate of the binary fraction, and a low reddening to avoid the effect of differential reddening. This is a sample of current magnitude diagram that we obtained in which we can see that the quality is excellent, and in particular, for example, in this case of PAL 12, we can see that the binary sequence is clearly well distinguishable from the cluster main sequence, and I estimated that the error is lower than 1 cent at magnitude 22.5. So the method is the same that I outlined before. We populated the cluster mirage line, assuming an initial mass function, and we taking into account for photometric errors and incompleteness by performing a number of artificial stars experiments. And this how to simulate the population of single stars. Then, by assuming a mass ratio distribution, we simulated also a population of binaries in a variable fraction. And then, using the galactic model of Robben et al., we simulated also the field population. By merging all these three color magnitude diagrams, we obtain a simulated color magnitude diagram that can be directly compared with the observed diagram of a given cluster. This is an example for M55. And a chi-square procedure has been carried out to minimize the difference between the ratio of the stars populating a binary sequence and the cluster main sequence stars. This method is very powerful, since here we can see that the uncertainties associated to this measure is about 1%. That is very accurate if we compare it with the value that is obtained from radial velocities analysis. So the results of this. Yes, that in global cluster is. If you have several, well, the problem is that if you have several populations, you can do the same work, but okay, the results cannot be accurate since the main sequence of another population can overlap the location of the binary sequence. So in practice, this method can be applied only to globular clusters to have a good estimate of the binary fraction. But in this case, globular. Well, of course, yes. This is, for example, the case of omega Sen or other clusters that have been proposed to have multiple population. In this case, the fractional binaries could be contaminated. But in honest clusters, this should not occur. So the results, these are two plots in which the binary fraction is plotted against two cluster parameters, in particular the age and the integrated magnitude. So the main results is that the bulk of the sample we analyzed have a binary fraction that is about 13% with a very small dispersion. So presents a very similar fraction of binaries. But there is also a group of 4 clusters which have a binary fraction that is significantly higher, which range between 30 and 50%. Now, apart from the absolute value of the binary fraction we estimated, that is also dependent on the assumed distribution of mass ratio and on assumed MMF, this sample can be used also to look for correlation between the fractional binaries and the various cluster parameters in order to understand which are the processes which lead the fractional binaries during the evolution of the cluster. So, if we correlate these values with the various cluster parameters, we observe 2 significant correlations that are the 2 that are shown here. In practice, there is an anti-correlation with the cluster age, in the sense that younger clusters have a higher binary fraction, and another correlation with the integrated luminosity that talks about mass in practice. And in particular, the smaller clusters have binary fraction that is higher. However, 13 is not a large number, so this sample is relatively small. And here we can see that the same cluster that produce the correlation with age are the same 4 that produce the same correlation with mass, since they are at the same time the smaller ones and the younger ones. So here it's difficult to distinguish which parameters drive the binary fraction. However, a recent study by Milone et al. Enlarged the sample to 60 globular clusters and confirmed the anti-correlation with the absolute magnitude, while find only an insignificant correlation with age. So at least the correlation with the cluster mass seems to be real. Now, to understand what is the physical reason of this correlation, we need to look at also the theoretical framework that up to now has been carried out by using 2 different approaches. In particular, one is the use of n-body simulation, in which the orbits and the interaction between the stars in a globular cluster are calculated directly using supercomputers. These are simulations that are very powerful, but have the problem that are very CPU consuming. And so up to now, until now, there are only one work, that is this one of Harley et al. 2007, in which more than one simulation is shown. And in this case, there are 4 simulations that are very few to understand the effect of the environment in the evolution of the binary fraction. Another approach is faster. It is based on Monte Carlo simulation. In practice, there is a simplified treatment of the interaction. And there is a random generation routine that takes into account for the statistical properties of the population of single stars and binary stars. But also in this case, there are only sparse simulations which are performed with different assumptions. And in particular, the results that are obtained are conflicting with the n-body simulation. So in practice, we cannot use also these results to constrain the parameter space to understand which are the parameters that are important for the evolution of binaries. So we did propose, I developed an analytical code that is based on a completely different approach, in which both the interaction and the dynamics of in the clusters are treated in a statistical way using a number of simplification in the analysis of the various processes of binary formation and destruction that are performed inside an environment that is constituted by a dynamical evolving globular cluster. Now, I want to stress now that this approach is less, how can I say, is worse than the one of n-body simulation, for example. Since here there are a number of approximations that in n-body models are taken into account in an accurate way. But, however, this approach can be useful since it's faster and, in general, can reproduce the results of n-body simulation in a qualitative way. And so, it's possible to span a wide range in initial conditions that allow to draw some conclusion about the importance of the various processes and of the various parameters in the evolution of the binary fraction in globular clusters. Now, I give an overview, a quick overview of the various processes I took into account. One process is the process of tidal capture that occurs when two single stars approach with small impact parameters and a small relative velocity component. This produces the fact that the two binaries pass from a free state, the two stars pass from a free state to a bound state, so forming a binary stars. Another process is the process of ionization that occurs when a binary star collides with a single star, so with another binaries, and part of the kinetic energy of the colliding object is transferred to the binary system that can be broken by this interaction. So starting from a single stars and the binary stars forms three single stars. Other process, the process of exchange, occurs when there is a collision between stars with a hard binaries under particular condition. In this case, there is a formation of an unstable triple system with ejection of the less massive components. In this case, so there is an exchange between the colliding stars and one of the two components of the binary system. And then I also took into account the stellar evolution, since both single stars and stars in binaries evolves, and this can produce various outcomes, like, for example, the breaking of the binary system due to the explosion, for example, in supernova 2, if the dominant component is a massive star. Or, for example, the merging between the components of the binary system. Another important process is the process of evaporation from the clusters. That is a consequence of the efficiency of the energy equipartition, kinetic energy equipartition. In particular, when collision becomes important in the clusters, the less massive stars gain more velocity and so are easily ejected from the cluster. So in general, since binary stars are on average more massive than single stars, this can produce a relative difference between the fraction of binaries and single stars. And on the basis of the same process, there is the mass segregation effect. In practice, for the equipartition of kinetic energy, the binary stars that are in general more massive tends to sink into the core of the cluster, so producing a radial gradient in the abundance of the binary fraction. As I told you before, this is considered within a globular cluster that dynamically evolves. So in general, when a cluster evolves via losses of stars and relaxation tends to collapse, and this collapse can be halted partially by the presence of a significant fraction of hard binaries. So I run a number of simulations, about 40 simulations, with different initial conditions. In particular, with different initial cluster central density, different central velocity dispersion, a different fraction of primordial binaries, and a different efficiency of the evaporation. Now, this is the result for a particular model that have been run with 10 up to the third solar masses per cubic parsec of density, central velocity dispersion of 5 kilometers per second, a primordial binary fraction of 50%, and an efficiency of the evaporation of 5% for gigayear. So here we can see a clear trend in the evolution of the binary fraction. In particular, the fraction of binaries tends to decrease suddenly in the first gigayear of evolution. And this behavior is followed by a constant and slow increase of the fraction of binaries up to the end of its evolution, so after an Hubble time. The dashed line indicates the same behavior but in the core of the cluster. And here we can see that the fraction of binaries is higher due to the fact that following the mass segregation, binary stars tends to go in the core. So even if the behavior is the same, the absolute fraction of binaries is higher in the core. To understand this behavior on physical basis, we can look at another plot that is a bit more complicated, but represents the derivative of the fraction of binaries versus time. This derivative is particularly important since can be seen as the sum of the contribution of the various processes. So here the black line that is here represents the sum of all the contributions, while the blue line that in practice overlap the black line in the first 3 gigayears of evolution represents the contribution of ionization process. That here we can see that is dominant in a cluster evolution. This can be explained by a simple fact. In practice, when we define a population of binaries, part of this population of these binaries have a binding energy that is on average lower than the mean kinetic energy of the objects in the cluster. So in a collision, it's easy that the colliding object transfer energy to the binary system. And so these systems are more easily broken via the ionization process. And in practice, they are broken whole in the first gigayear of evolution. But after this first gigayear, in the cluster remains only the hard binaries, so those binaries would have a high binding energy. And so in practice, in collisions, tends to shrink and not to be broken. And so in practice, the efficiency of the ionization process drops to 0. Another important process is the process of evaporation, that is indicated with a red line, that tends to increase the fraction of binaries in a constant way. And this is, as I told you before, the consequence of the fact that when evaporation is important, it's easier to eject from the cluster single stars rather than binary stars that are more massive. So in practice, this tends to make an increase of the binaries in a constant way. And all the other processes that are represented by the green line, which stands to 0 during all the evolution, are in practice negligible. So this is a picture of some of the models that I run with different initial parameters. And this, here we can see that while the general behavior of the binary fraction is similar in all models, the absolute value of the binary fraction can change in a significant way after enable time, so at the end of the evolution, or at the end of the simulation. And so an obvious dependence is the dependence of the initial fraction of binaries. Of course, if I start a simulation with an higher fraction of binaries, I will arrive with an higher fraction of binaries. But other dependence is the dependence on the evaporation, and in particular, system with much more efficient evaporation ends their evolution with the surviving fraction of binaries that is in general higher. But a more complicated dependence is the dependence on the other structural parameters, in particular the density and the central velocity dispersion. So here is a map of the surviving fraction of binaries for models which starts with the same primordial fraction of binaries. So this is the results after enable time. Here there are the simulation for different efficiency of evaporation, and the results in the core or in the whole cluster. But in general, one can look at one of them or whatsoever, since the behavior is similar. And here we can see that there are clear variation. In particular, the darker contours indicates higher fraction of binaries. In particular, here we can see that the fraction of binaries decrease by increasing the central density, and decrease also by increasing the central velocity dispersion. The reason at the basis of these results is linked to the efficiency of the ionization process, that is the dominant process in the evolution of binaries. In particular, when the cluster central density increases the number of collisions. And when increase the velocity dispersion, increase the energy of the collision. So in practice, the efficiency of the ionization increases as these two parameters tend to increase. And this produces this effect that is visible. Curiously, this is the same dependence that have the mass of the clusters on the same two parameters, since when the density is higher, of course, the mass is higher. And when a cluster with a higher velocity dispersion, for a consequence of the real theorem, tends to have larger masses. So, in particular, if we plot the fraction of surviving binaries as a function of the mass of the system, we observe this anticorrelation that is, of course, linked to the fact that I told you now, in practice, the efficiency of binary ionization and the cluster mass have the same dependence of the cluster structural parameters. And this is the same evidence that I showed you based on the analysis of the 13 globular clusters of the paper Sollima et al. 2007, and the same that have been observed by Milone et al. 2008. So, in practice, even with a very simplified approach of the evolution of the globular cluster, we are able to reproduce the main observational evidence on the evolution of the binary systems in globular clusters. The future of this project will be to extend the analysis of the measure of the binary fraction to a sample of open cluster, and this is particularly important since open clusters are similar to globular clusters but are smaller and younger. So if this hypothesis is true, we expect to see a continuous trend of the group of open clusters with respect to those of globular clusters, and in particular this cluster should have a higher fraction of binaries. And the other thing that we plan to do is to study the radial distribution of binaries in those globular clusters where we already have ACS observation with a wide field photometry, and this to study also the radial distribution of, binaries with respect to single stars to check if the process of mass segregation is efficient, in particular in the external part of the cluster where collisions are less important. I finish. Okay. Very quick.
Thank you very much for your talk. So it's time for questions. Okay.
Can you give the mass range for your binary fraction, please?
The mass range for? Well, here, of course, you mean the mass of the binary system, or the mass of the cluster?
Yeah, the mass of the binary, the total system.
Well, in general, the binary can have an overall mass that cannot be more than 1.6, or mass, the sum of the two components. Since the mass of the turnoff are 0.8, so even in a case of equal binaries, we are right, 1.6.
I guess it's related to this question is, you hadn't mentioned what are your hypotheses in the distribution of masses of the stars in the globular cluster, and also both in the estimate of the binarity from the cluster. Mm-hmm. And in the simulations, you have to assume a ratio, a distribution of ratios of masses. Could you comment on that?
Yes. Well, regarding to the observational part, so the first part of the talk, we try to assume different mass ratio distribution to see how the fraction of the derivative fraction of binaries can change based on this assumption. And so we tried various mass ratio distribution, both assuming that there are random association between stars, or assuming a mass ratio that is peaked toward the high mass ratio or peaked toward the low mass ratio. In general, for the group of clusters that have a low binary fraction, so 13%, the clump, the result is not very sensitive and, can change of 2 or 3%. The results can change much when the binary fraction is higher. But in general, the trend with age and with luminosity is even hold in any case. In the case of the simulation, of course, one have to assume a distribution of mass ratio. But however, I try to do some simulation with different mass ratios, and in general, the trend don't change. Since the trend is here in this case is based on the ionization efficiency, so I have only a smaller dependence of the mass ratio distribution.
Any other question?
I actually have two questions. First one is how does the mass distribution vary with time in your simulations?
Well, okay, this is an output of the simulation. Well, if I to be sincere, I didn't look at it, but okay, I know that of course this depends also on the location where you are looking, since of course there's the effect of mass segregation. So you see a different IMF in the central part or in the other part. In general, you see the depletion of the low mass stars that are easily ejected from the system. But okay, I have to look it better since it was out on the scope of the papers in this case.
And the second question is that perhaps the high mass cut you put on the mass distribution you just mentioned is perhaps a bit small because CV systems, for example, they end up having a total mass relatively small, more or less the one you mentioned, something like 1.5 solar mass in total. But originally they're more massive. So you may...
No, but okay. But the original, okay, the mass function starts with the normal Krupa mass function. So up to 120 solar mass in general. But okay, of course, after a few mega years, all these massive stars go down. So at the end of the evolution, when past double time, the binaries are on general cannot be more massive than 1.6. But in the
so that
beginning of the simulation, yes, that could
be. So that 1.6 was nowadays.
Yes, nowadays.
Okay.
Yes, okay.
Sorry,
no.
I misunderstood.
No, of course. No, sorry.
Any other question? If not, then let's thank the speaker again.